Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of siege weapons. Please like and subscribe for more restful content. Now, let's begin. The first siege weapons emerged not from grand armies or master engineers, but from necessity. As early humans began to gather behind walls of stone and clay, defense transformed from instinct into architecture. Those who attacked learned quickly that persistence and brute force could not always breach what human hands could build. Thus began the slow, deliberate science of overcoming barriers. In this earliest period, warfare was as much about patience as strength. A fortified village could hold for weeks, its defenders relying on stored grain and faith, while the attackers camped outside in the dust and waited. Siegecraft, in its infancy, was the art of endurance. Archaeological evidence points to Jericho as one of the first walled cities, dating back nearly 10,000 years. Its walls, thick with stone and mud brick, were not merely symbolic boundaries, they were obstacles to be solved. The very existence of those barriers forced aggressors to think differently. The attackers of Jericho and similar Neolithic fortresses likely employed nothing more sophisticated than ramps, ladders, and fire. Yet even then, an understanding of material limits began to form. The weight of a stone wall could be turned against itself with enough pressure applied at the right point. Water, if diverted or dammed, could erode foundations. In these moments, the first engineers of destruction began to observe the interplay of physics and persistence. The Assyrians, rising in the first millennium BCE, brought system and precision to siege warfare. Their campaigns were meticulous, recorded in stone reliefs that depict battering rams, siege towers, and sappers undermining walls. The battering ram, a beam suspended by ropes and swung rhythmically, was as much an instrument of engineering as of violence. Its effectiveness depended on resonance, the ability to strike repeatedly at a structure's natural frequency until it yielded. Behind the wooden frame of the ram, soldiers understood intuitively what later scientists would formalize: that energy applied rhythmically and consistently could cause catastrophic failure in even the strongest materials. This mechanical rhythm was supported by logistics. Siege warfare required resources on a scale far greater than open battle. Armies needed to feed thousands while they waited outside walls that might never fall. The early Assyrian engineers calculated the tension of ropes, the slope of earthen ramps, and the height necessary for towers to meet a city's parapet. Their mastery lay in translating mathematical precision into physical structures under immense pressure. When one ramp crumbled or a tower burned, they built another. Each attempt refined their craft. Every failed assault taught them something about leverage, weight distribution, or flame resistance. By the time the Greeks inherited these principles, the art of the siege had become a discipline. The polis, with its emphasis on city walls and defense, gave rise to a new generation of thinkers who viewed war as an experiment in applied geometry. Greek engineers like Polyidus and Diades, the latter reputed to have served Alexander the Great, expanded on the Assyrian foundations with devices of striking complexity. They introduced torsion-powered mechanisms, early precursors to the ballistae, which relied on twisted sinew or hair to store potential energy. When released, this energy converted into a violent, focused force capable of hurling stones or bolts with precision. The transition from brute impact to mechanical projection marked a turning point in siege technology. It revealed a shift from muscle to mathematics, from repeated blows to calculated trajectories. These machines were not only built but tuned, their chords adjusted for temperature, humidity, and elasticity. The builders became part physicist, part musician, listening for the harmony between energy and matter. The result was a weapon that combined science and spectacle, a demonstration of what humans could create when necessity and intellect aligned. The ancient city of Tyre, besieged by Alexander in 332 BCE, stands as a testament to this growing sophistication. Situated on an island, it appeared untouchable. Yet Alexander ordered the construction of a massive causeway, hundreds of meters long, built from rubble and timber to reach the city's walls. His engineers devised mobile siege towers taller than the defences they faced, outfitted with catapults and archers to suppress the defenders above. What had once been a simple question of how to breach a wall had evolved into a comprehensive system of engineering, logistics, and psychological warfare. The causeway itself became a weapon, transforming geography into an extension of the army. In these moments, the siege ceased to be merely a military act. It became a laboratory for applied science. Every structure razed or destroyed offered new data about load-bearing capacity, thermal resistance, and the strength of materials under stress. The engineers who worked in the dust of these sieges were, in their own way, the forebears of civil and mechanical engineering. They studied failure not to mourn it, but to learn from it. The collapse of a tower or the splitting of a ram's frame revealed truths about balance and stress distribution that would echo through the centuries. As night fell over those ancient camps, fires flickered against the ramparts, and the air grew still. Soldiers dozed beside their machines, while the engineers sketched improvements by firelight, altering pulley ratios, strengthening supports, adjusting the curvature of a projectile arm. Siege warfare demanded patience and precision, qualities rarely celebrated in battle, but essential for victory. And while history remembers the kings and conquerors, it was these anonymous thinkers who made conquest possible, turning raw power into calculated inevitability. By the end of the classical period, the principles of siegecraft had matured into a science of controlled energy. Whether through the steady rhythm of the ram or the sudden release of the ballista, every strike and launch was an experiment in physics. The knowledge accumulated through centuries of trial and adaptation laid the groundwork for what was to come. The towering engines of Rome, the intricate trebuchets of the Middle Ages, and eventually the thunderous arrival of gunpowder. The story of siege weapons begins not with destruction, but with curiosity. To breach a wall was to understand it, to study its composition, its weaknesses, and its endurance. Each weapon born from this pursuit carried within it the quiet logic of problem solving, and as the centuries advanced, the siege would remain a proving ground for humankind's endless desire to solve the impossible. When Rome rose from the fragmented world of city-states and kingdoms, it inherited both the science and the patience of siegecraft. The legions of Rome were not only soldiers, but builders. Each campaign a moving workshop of carpenters, engineers, and mathematicians. Their weapons, though fearsome, were designed with the calm logic of civil architecture. The same minds that built aqueducts and roads also built machines to unmake the walls of others. Siegecraft was, in Roman hands, not chaos but procedure. The Romans refined the torsion-based catapult, known as the ballista, and expanded its applications. These machines could launch heavy stones to batter walls or iron-tipped bolts to pierce armour at range. They relied on bundles of twisted sinew, often from animal tendons, whose tension could be precisely adjusted. The Romans measured that tension with meticulous care, noting that humidity or cold altered performance. This level of observation blurred the line between engineering and experimentation. Each siege became a data point in an evolving understanding of mechanics. Reports from campaigns were circulated and analysed, ensuring that the next engine was always stronger, more efficient, and easier to deploy. The Roman onager, or wild ass, derived its name from the violent kick it gave upon release. Unlike the ballista, which used two arms, the onager relied on a single arm driven by torsion. The simplicity of its design allowed it to hurl large stones with tremendous power, though its recoil made it unpredictable. Roman manuals recorded the need for strong foundations and recommended setting the frame in sand to absorb the shock. Every recommendation reflected experience, what today might be called empirical science. Through countless sieges, these refinements turned destruction into a methodical craft. The most remarkable aspect of Roman siegecraft was scale. Their operations could extend for years, surrounding cities with lines of fortifications that mirrored those within. The siege of Alesia in 52 BCE demonstrates this precision. Julius Caesar's legions constructed two concentric rings of fortifications, one to contain the Gallic defenders, another to repel external reinforcements. The inner wall stretched for 10 miles, the outer for 14, complete with towers, ditches and traps. These were not mere barriers but interlocking systems of defence, built under pressure, coordinated across terrain and completed in weeks. Each section was standardised, each component measured. It was the manifestation of organised intelligence applied to war. The engineers who directed these constructions often held equal rank to field officers. They calculated the trajectory of missiles, the angle of ramps, and the resistance of timber under stress. The principles guiding their work foreshadowed modern mechanical theory. To hurl a stone effectively required understanding potential and kinetic energy. To breach a wall required studying its load-bearing structure. While these concepts had not yet been expressed mathematically, Roman practice was rooted in the same reasoning that would later define physics: the conversion and control of energy through predictable systems. The discipline of siegecraft also shaped Roman society beyond the battlefield. The logistical systems necessary to sustain prolonged sieges demanded precision in supply and communication. Grain depots, water channels and medical stations were arranged with geometric regularity. Each campaign tested the empire's capacity to coordinate thousands of people and resources toward a single, measured goal. It was a demonstration of control, not just of territory, but of process. The Roman army's capacity for order became its most formidable weapon. Roman engineers left behind detailed writings on their craft, though many have been lost. Vitruvius, the architect and engineer of the 1st century BCE, preserved fragments of their knowledge in his treatise De Architectura. He described machines for lifting water, constructing buildings, and launching projectiles, each based on proportion, balance, and the manipulation of force. Vitruvius saw no distinction between the peaceful and the destructive uses of engineering. To him, both were manifestations of the same principles. The catapult and the aqueduct were products of one intellect, a rational mind observing the behaviour of matter and designing accordingly. In time, however, the Roman mastery of siegecraft revealed its own limits. As the empire expanded, it encountered fortifications of increasing sophistication, from the walled cities of the east to the stone citadels of the Celts and Germans. Each required adaptation. The Romans built taller towers, heavier rams, and longer-range engines. But no matter how powerful the machines became, victory depended on endurance. Many sieges turned into contests of will rather than force. Disease, weather, and supply shortages became as decisive as any mechanical advantage. In these drawn-out struggles, the science of siege met the reality of nature's resistance. When the empire began to fragment, its knowledge dispersed with it. The great libraries of engineering declined, and with them much of the recorded precision that had defined Roman warfare. Yet the tools themselves did not vanish. Their designs were copied, altered, and adapted by the Byzantines, Persians, and later the medieval kingdoms that inherited the remnants of Roman expertise. Through these transformations, the essence of siege science endured, the manipulation of materials to overcome obstacles. The fall of Rome did not mark an end to siege technology, but a transition. The emphasis shifted from torsion to traction, from the coiled sinew of ancient engines to the weighted arms of mechanical trebuchets. This change reflected not a loss of sophistication, but a change in available resources and priorities. Where Rome had relied on standardized manufacture and centralized organization, the medieval world relied on local innovation. Each fortress and army became a workshop of experimentation, rediscovering in pieces what Rome had once systematized. The legacy of Roman siegecraft lay not only in its machines but in its mindset. The careful documentation, the standardization of construction, the rational division of labor, all of these became templates for later military and civil engineering. The Roman siege was not chaos, it was a geometry of intention. The same mental structure that built roads straight across continents applied itself to the breaching of walls. In this way, Rome transformed siege warfare from an act of destruction into an instrument of civilization's spread. By the time the last Roman garrisons withdrew from their frontiers, the principles they had refined were already taking root elsewhere. The art of the siege had become a dialogue between offense and defense, a continuous evolution driven by observation and necessity. What began as the simple desire to breach a wall had become a science of measurement and prediction. The empire that once encircled the Mediterranean left behind not only ruins, but a method, one that would be reinterpreted by every civilization that came after. When the Middle Ages began to take shape across the ruins of Rome, so too did a new era of siege technology. The torsion engines of antiquity, reliant on sinew and precision manufacture, faded as resources and central organization declined. In their place rose a weapon both simpler and more powerful, one that used not twisted fiber, but gravity itself. The trebuchet, emerging between the 6th and 12th centuries, became the defining siege engine of the medieval world. It was at once elegant and terrible, its motion silent until the moment of release, when physics spoke in the crash of stone on stone. The trebuchet's genius lay in its simplicity. Unlike the catapult or onager, which stored energy through mechanical strain, the trebuchet harnessed the steady, predictable force of falling mass. A long beam pivoted on an axle, one end weighted with stones or lead, the other holding a sling that cradled the projectile. When the counterweight dropped, it pulled the beam through a controlled arc, accelerating the sling and launching its payload with remarkable precision. The physics were direct. Gravitational potential energy converted into kinetic energy through leverage and timing. This principle, pure, consistent, and scalable, made the trebuchet one of the most reliable and destructive weapons ever built before the age of gunpowder. Medieval engineers quickly learned that the trebuchet could be tuned. The length of the arm, the ratio between its long and short sides, and the mass of the counterweight determined both range and impact. Adjustments could transform the weapon from a wall breaker to a tool of harassment. Smaller traction trebuchets, powered by men pulling ropes, appeared first, likely of Chinese or Near Eastern origin. Their European descendants evolved into the massive counterweight trebuchets that dominated the sieges of the 13th and 14th centuries. Each represented a step toward greater precision in the application of force. The construction of a trebuchet was an act of engineering discipline. Teams of carpenters, blacksmiths, and rope makers worked together to assemble beams as thick as a man's body and ropes woven from animal hair or hemp. The geometry of the frame had to balance stability with motion. Too rigid, and the machine might shatter under stress. Too loose, and it would waste energy in sway and vibration. Engineers observed how energy travelled through each component, learning intuitively to reinforce stress points with iron bands and cross braces. Every successful launch was a proof of concept. Every failure was a study in mechanical stress. One of the most famous trebuchets in history, Warwolf, was built by order of King Edward I of England during the siege of Stirling Castle in 1304. Contemporary accounts describe it as so large that its assembly required months, and its stones weighed more than 150 kilograms. The Scottish defenders, seeing it rise from the plains, reportedly offered surrender before it was even used. Edward refused until Warwolf had fired, demonstrating that siegecraft had become as much psychological as physical. The slow construction of such machines, the visible rise of wood and iron against the skyline, projected inevitability. The defenders saw in it not only the weapon, but the discipline and determination of those who built it. The trebuchet also introduced a new relationship between science and warfare. Its operation required an understanding of trajectory, angular momentum, and material strength long before those terms existed. Engineers tested different sling lengths, projectile shapes, and release angles. They observed that round stones travelled farther but struck with less stability, while irregular ones caused more damage to walls. Some experimented with incendiary or diseased projectiles, turning the trebuchet into an early tool of biological warfare. Each experiment contributed to a growing empirical understanding of motion and force, principles that, centuries later, would become the foundation of Newtonian mechanics. The trebuchet's dominance coincided with a transformation in fortification design. Castles grew thicker, rounder, and more complex. Builders learned to deflect rather than resist impact, using curved walls and layered defences. In response, siege engineers developed heavier counterweights and refined aiming systems. Ropes and pulleys allowed fine adjustments to angle and elevation. Some machines incorporated winches that preloaded the sling for faster reloading. The contest between wall and weapon became a dialogue of adaptation. Each new fortress invited innovation. Each new engine provoked evolution in architecture. The science of the trebuchet extended beyond battlefields. Scholars of the period, particularly in the Islamic world, studied its principles as part of a broader interest in mechanics. Writers such as Ismail al-Jazari and later European thinkers recorded detailed treatises describing proportions, counterweight calculations, and construction methods. These manuscripts reveal the growing realization that the trebuchet was not merely a tool of war, but a demonstration of physical law. In some texts, it was even used as a teaching device to explain motion and gravity centuries before Galileo. The operation of a trebuchet was also a performance. Teams of men worked in rhythm to reset the sling, hoist the counterweight, and prepare the next shot. The successful launch required coordination and timing akin to a ceremony. The sight of a stone rising soundlessly into the sky, pausing at its arc before descending toward the target, carried an almost hypnotic inevitability. The calm precision of its motion, the brief suspension before impact, lent the weapon an eerie dignity. To watch a trebuchet at work was to witness the controlled transformation of energy, order producing chaos. Over time, trebuchets became larger, their stones heavier, their frames more elaborate. The largest could hurl half-ton projectiles over 300 meters. Yet despite their power, They represented the end of an age. Even as Europe perfected them, new discoveries in chemistry and metallurgy were preparing to redefine warfare. Gunpowder, already known in China by the 9th century and spreading slowly westward, would soon offer a more compact source of stored energy. Where the trebuchet relied on gravity, the cannon would rely on combustion. The shift would be decisive, but it would not erase what the trebuchet had taught, that victory lay in understanding matter and motion. By the 14th century, trebuchets still stood beside early bombards, both used in the same sieges. But within a century, the cannon's roar replaced the trebuchet's silent arc. The medieval engineer's mastery of leverage and balance gave way to new studies in pressure and recoil. Yet the trebuchet left an enduring legacy. It had demonstrated that natural forces, when harnessed through design, could be predictable and powerful. It showed that war could be guided by mathematics as much as courage. In its long arc from invention to obsolescence, the trebuchet embodied a truth that would persist into the modern age. Technology changes, but the pursuit of mechanical understanding does not. As night settled over the encampments of medieval Europe, the silhouettes of trebuchets loomed like monuments of wood and rope against the firelight. Their builders rested beside them, aware that each machine was both a weapon and a lesson. The trebuchet marked a point in history where science, craftsmanship, and human intent converged into motion, where gravity itself was invited to join the battle. The arrival of gunpowder transformed siege warfare more completely than any invention before it. What had once depended on leverage, torsion, or gravity now drew its power from combustion, the rapid release of chemical energy confined within metal. The shift was neither sudden nor uniform. For nearly 2 centuries, trebuchets and bombards stood side by side on the same fields, their engineers studying one another's work. Yet as the 15th century progressed, the thunder of cannon began to drown out the quiet rhythm of ropes and counterweights. Siegecraft entered its most explosive age. Gunpowder, a mixture of saltpeter, charcoal and sulfur, had been known in China since the 9th century. It travelled slowly west through trade, adaptation and rumour. By the early 1300s, European alchemists were experimenting with it, first for fireworks and later for propulsion. The earliest siege guns were crude, iron or bronze tubes bound with hoops, fired from wooden frames. Their accuracy was poor, their loading dangerous, and their explosions unpredictable. Yet even these unreliable weapons offered something new, a way to concentrate energy beyond what muscle or gravity could supply. The concept of stored mechanical energy gave way to chemical reaction, an irreversible transformation that released power in an instant. The first effective bombards appeared in the 14th century. They were immense cylinders of cast bronze, sometimes weighing several tons, firing stone balls larger than a man's head. Their names reflected their presence: Mons Meg, Dulgrit, and Pumhart von Steyr. These machines were less portable than trebuchets, but vastly more destructive. The impact of a single stone ball, propelled by the detonation of gunpowder, could shatter the strongest medieval walls. Their recoil carved trenches into the earth. Their smoke hung in the air like a new kind of weather. With them, war began to sound different, louder, more final, less human. At first, cannon were unpredictable instruments. The metallurgy required to contain repeated explosions was still primitive. Gun barrels burst, fragments killed their operators, and charges varied in strength. But the same empirical mindset that had refined the trebuchet now turned to chemistry and casting. Metallurgists studied the effects of alloy composition and cooling rates. Powder makers experimented with grain size and moisture content to regulate burn rate. What emerged from this collective trial and error was not only a more reliable weapon, but an early form of scientific standardization. Measurements of bore diameter, projectile weight and powder charge became as precise as any formula in later physics. The transformation of fortifications followed immediately. The vertical stone walls that had defined medieval castles were no match for cannon fire. Masonry cracked under the repeated percussion of iron and stone. In response, architects developed the tres italienne, the Italian style of fortress, characterized by low, thick, angled walls of earth and brick that absorbed and deflected impact. Bastions extended outward in geometric patterns, creating overlapping fields of fire. The entire landscape of defense became a mathematical problem. Angles, distances, and lines of sight mattered as much as courage or numbers. Siege warfare had become geometry set in stone. The great sieges of the 15th and 16th centuries demonstrated this new logic. At Constantinople in 1453, the Ottoman engineer Orban constructed massive bombards for Sultan Mehmed II, capable of firing projectiles weighing over half a ton. For weeks they pounded the ancient walls that had withstood centuries of attack. When they finally broke, it was not brute force alone that triumphed, but the systematic application of material science. Gunpowder, casting, and design combined into precision. The fall of Constantinople marked more than the end of an empire. It marked the beginning of a technological order in which chemistry and engineering determined the fate of cities. Cannon evolved rapidly. Stone shot gave way to cast iron balls, smaller but far denser. Bronze barrels yielded to wrought iron and later to cast iron, which was cheaper and more uniform. Artillerymen learned to calculate elevation and range, adjusting charges for distance and trajectory. Instruments for measurement appeared: quadrants, calibers, and tables of fire. By the 16th century, artillery was no longer experimental. It was systematic. Manuals were written, diagrams drawn, and mathematical treatises published. The science of motion, hinted at by the trebuchet's arc, now found its first quantitative expression in the paths of cannonballs. With the power of cannon came a new rhythm of warfare. Sieges that had once lasted months could be decided in days. The slow, methodical pressure of medieval encirclement gave way to concentrated bombardment. Walls that had taken years to build crumbled under hours of fire. Yet the efficiency of the cannon did not make siegecraft simpler. It demanded new logistics: transport for heavy guns, powder magazines, shot furnaces, and specialized crews. Each battery was a small factory, consuming metal and saltpeter at industrial scale. Warfare had begun to resemble production. The psychological effect of artillery was as decisive as its mechanical one. The thunder of bombardment carried for miles. It announced presence, power, and inevitability. Defenders faced not the slow rhythm of engines, but the shock of explosions that arrived without warning. Chroniclers described walls trembling, air vibrating, and men rendered deaf and disoriented. The sensory impact of gunpowder altered not only tactics, but perception. War had entered the age of shock. Engineers, too, changed their role. Where once they had worked close to the machines, pulling ropes and balancing arms, they now stood apart, calculating trajectories and supervising crews. Mathematics became their primary tool. The cannon turned warfare into a field experiment in applied physics. Each shot an equation, each impact a data point. As early as the 17th century, thinkers like Galileo and Tartaglia used cannon fire to study projectile motion, measuring angles and distances to derive the laws of acceleration and parabolic flight. The battlefield became an open-air laboratory. Even as the cannon became dominant, the principles of older siegecraft survived within it. The management of weight, the balancing of force and resistance, the understanding of structure under stress, all persisted, only reframed through new materials. In essence, gunpowder had not replaced the science of the siege. It had condensed it. Energy was no longer stored in ropes or counterweights, but in powder and containment. The logic remained, to convert potential into motion with precision and control. By the late Renaissance, artillery had matured into a system of knowledge. Engineers trained in geometry and metallurgy as rigorously as architects or astronomers. Fortresses spread across Europe in perfect star shapes, each bastion calculated to minimize blind spots and maximize fields of fire. The dialogue between wall and weapon continued, only now it was spoken in the language of mathematics and chemistry. Every advance in offense provoked a response in defense, and every adaptation deepened the understanding of physical law. As evening fell over the sieges of this new era, the flicker of flame within cannon mouths cast brief light across fields of smoke. The silence between shots was heavy, filled with the smell of sulphur and iron. The age of the trebuchet had ended, but its lessons endured: discipline, observation, and the relentless search for improvement. The science of siege weapons had become inseparable from the science of nature itself. In every echo of a cannon's roar, one could hear not just destruction, but the measured rhythm of discovery. The explosion of gunpowder artillery forced a revolution not only in offence, but in defence. The once impregnable towers and curtain walls of the medieval castle, designed to resist the patient hammering of trebuchets, now crumbled under a few days of concentrated bombardment. The old vertical defences magnified the kinetic force of incoming shot. Walls shattered, towers toppled, and stone splinters turned the air itself into a weapon. The survival of cities required a new geometry, one designed not to defy physics but to work with it. This geometry took form in the 15th century as the trace italienne, or bastioned fortress. Originating in Italy and spreading rapidly across Europe, it replaced height with depth and hardness with absorbency. Engineers lowered walls, thickened them, and surrounded them with sloping earthen banks that could absorb impact rather than fracture. Ditches widened, bastions projected outward, and parapets angled to deflect rather than resist. These new fortresses resembled vast symmetrical stars when viewed from above. Each bastion covered its neighbour with overlapping fields of fire, eliminating blind spots. The fortress had become an equation, each line, slope, and distance carefully measured against the arc of artillery. This transformation was not aesthetic, but mathematical. The ideal fortress required precise ratios between wall height, bastion length, and ditch depth to balance visibility, fire coverage, and structural strength. Engineers such as Francesco di Giorgio, Michel Sanmicheli, and later Sébastien Leprestre de Vauban developed treatises to formalize these proportions. Their designs represented the first large-scale application of geometry to practical engineering. The fortress became both a scientific instrument and a statement of rational order. To construct one was to demonstrate mastery over form and function, the same principles that governed bridges, cathedrals, and machines. Vauban, serving under Louis XIV in the 17th century, brought this science to perfection. His fortifications, built across France and its borders, embodied system and predictability. He treated every site as a problem in physics. Terrain, soil composition, and artillery range were analysed before the first stone was laid. His walls sloped at precise angles to deflect shot. his bastions aligned with such regularity that they resembled geometric diagrams drawn on the earth. Vauban's genius extended beyond construction to the art of attack. He developed standardized methods for besieging his own designs: parallel trenches, zigzag approaches, and measured bombardment. For the first time, siege and defense were governed by the same principles of controlled geometry. The result was a paradox. The more scientifically perfect fortifications became, the more predictable warfare grew. A competent army with sufficient artillery and supplies could reduce almost any fortress given enough time. Victory depended not on courage or luck, but on endurance and method. The siege became a ritual of engineering rather than an act of improvisation. Attackers dug their trenches, established batteries, advanced by parallels, and applied measured fire. Defenders replied with countermines, sorties, and calculated intervals of resistance. Each side performed its role according to geometry. War had entered an age of symmetry. The influence of this geometry extended beyond the battlefield. The bastioned fortress reflected the ideals of early modern science: observation, measurement, and the search for universal principles. The same intellectual climate that produced Kepler's laws of motion and Galileo's experiments also produced Vauban's designs. Fortresses were laboratories of applied mechanics, their walls shaped by the same logic that described planetary orbits. The repetition of form, the precision of proportion, and the interplay of energy and resistance were expressions of a single worldview: that nature could be measured, predicted, and controlled. Constructing such a fortress required immense labour and organisation. Thousands of workers quarried stone, moved earth, and aligned walls by sighting instruments. Engineers tested soil compaction, measured angles with wooden quadrants, and calibrated cannon placements with line-of-sight calculations. The process combined manual skill and intellectual rigour in equal measure. When finished, a bastioned fortress could occupy several square kilometres and require decades to complete. Yet its beauty lay in restraint, not ornament. It was a functional landscape, every curve and contour justified by purpose. The star-shaped fortresses of the 17th century were also cities. Inside their walls lived soldiers, artisans, families, and administrators. Streets followed the same rational pattern as the defences, straight lines radiating from the centre, intersecting at right angles. The geometry of protection became the geometry of life. In this way, military design began to influence civil architecture. The fortress city symbolised security through order, a physical embodiment of the state's authority and rationality. To live within such walls was to inhabit a diagram of controlled force. Despite their strength, even these defences could not halt progress. As cannon improved and explosive shells replaced solid shot, the geometry of the bastion lost its invulnerability. By the 19th century, the introduction of rifled artillery and high explosives made even Vauban's fortresses obsolete. The energy of war had once again outpaced the structures built to contain it. Yet the intellectual legacy of bastion design persisted. Civil engineers adopted its principles of slope, reinforcement, and redundancy. Modern fortifications, from coastal batteries to underground bunkers, still trace their lineage to the measured logic of Vauban's lines. The Trace Italien also changed how armies thought about space. No longer was a fortress merely a static defence. It was a dynamic system integrated with surrounding terrain. Roads, rivers, and supply lines became part of the design, calculated for access and retreat. In this sense, siegecraft evolved into systems engineering. Victory was achieved not by overwhelming power, but by managing complexity. The fortress embodied the principle that resilience arises from balance, not resisting energy, but absorbing and redirecting it. As twilight settled over the bastion cities of early modern Europe, their outlines glowed faintly in the evening sun. Vast geometric shadows cast upon the land. Within their angles and slopes lay centuries of observation. The sum of lessons learned from trebuchets, bombards, and collapsing walls. They represented humankind's ongoing dialogue with energy, matter, and constraint. Every parapet and bastion was a conclusion drawn from experience, that the surest defence is not defiance but understanding. As the 17th century matured into the 18th, the thunder of cannon became not only the sound of war, but also the rhythm of scientific progress. Gunpowder had already changed the mechanics of siege warfare, but the precision with which artillery was used now depended increasingly on mathematics. The age of experiment turned into the age of calculation. No longer was it enough to simply aim and fire. Range, elevation, charge, and wind became measurable variables in a growing discipline that united the battlefield with the laboratory. The science of artillery was becoming a branch of physics. Early gunners had relied on tables built from experience, lists of angles and corresponding ranges derived from trial and error. These empirical charts were useful but limited, as they could not account for variations in powder quality, projectile mass, or barrel length. The 17th century saw the emergence of thinkers who sought to explain projectile motion through universal laws. Galileo, observing cannonballs rolling down inclined planes, deduced that motion followed predictable curves rather than straight lines. His conclusion, that a projectile followed a parabolic path under constant acceleration, gave artillery its first theoretical framework. War had produced an instrument of proof for natural philosophy. By the time of Isaac Newton, the connection between ballistics and physics was explicit. Newton's Principia Mathematica formalized the principles of motion and gravitation, providing the tools to calculate trajectories not only of cannonballs, but of planets. The same equations that described a projectile's arc could describe the orbit of the moon. Yet for all their grandeur, Newton's laws could not fully predict real artillery fire. Air resistance, wind turbulence, and powder inconsistency distorted results. The pursuit of accuracy therefore became a dialogue between theory and practice. Artillerymen observed where shots landed, mathematicians adjusted their formulas, engineers refined materials. Each discipline fed the other. This collaboration gave rise to the science of ballistics. Figures like Benjamin Robbins in the 18th century advanced it from speculation to quantification. Robbins invented the ballistic pendulum, a device that measured the velocity of a projectile by recording the momentum transferred to a suspended block. From this, gunners could calculate muzzle speed, optimize powder charges, and determine the efficiency of different barrel designs. For the first time, artillery performance could be expressed in numbers. What had been art was becoming engineering. Robbins' work influenced the Prussian and French armies profoundly. Military academies introduced mathematics, physics, and engineering into their curricula, training officers not only as tacticians, but as scientists. Jean-Baptiste de Gribeauval, the French artillery reformer, applied these principles systematically. His standardized cannon carriages and interchangeable parts reflected both industrial precision and mathematical discipline. Every component was measured, recorded, and manufactured to fit a unified model. The Gribeauval system transformed artillery into a rational tool, predictable, efficient, and mobile. When Napoleon rose to power, he inherited not only weapons but a culture of quantitative thought. Napoleon's campaigns demonstrated what this new science could achieve. His artillery officers used geometry and observation to coordinate fields of fire, adjusting trajectories with precision rarely seen before. Siegecraft, once defined by laborious earthworks, became an exercise in logistics and calculation. Batteries were emplaced at mathematically determined intervals. Ranges were measured with optical instruments. Elevation was set using protractors and plumb lines. Each bombardment was a controlled experiment in applied physics. The outcome of sieges at Toulon, Mantua, and Acre illustrated that victory now depended as much on computation as courage. As accuracy improved, so too did the materials of war. Metallurgists refined casting methods, producing barrels of uniform density and strength. Iron shot was replaced with spherical steel balls, and later with elongated shells that improved aerodynamics. Each change in form required recalculation of drag and stability. Artillery manuals grew thicker, filled with tables of fire, wind corrections, and powder coefficients. Engineers began to treat the cannon not merely as a weapon, but as a system, its barrel, powder, projectile, and environment interacting through measurable laws. The artilleryman's mind became a calculating engine. The influence of this mentality extended beyond the battlefield. The mathematical modelling of trajectories contributed to the development of calculus as a tool of analysis. The same differential equations that described cannon fire were later applied to celestial mechanics, hydraulics, and engineering design. The language of war thus entered the language of science. Each advance in destructive precision deepened humankind's understanding of motion, pressure, and force. The laboratory and the arsenal became indistinguishable in their methods: observation, measurement, refinement. The shift from static siege to mobile artillery redefined the very idea of a fortress. As guns grew more accurate and mobile, no fixed defence could guarantee survival. The once mighty bastions of Vauban's era became targets rather than refuges. The advantage passed to those who could move, calculate, and strike before the enemy could adapt. Siegecraft itself became less about walls and more about range. The line between mathematics and warfare blurred completely. To command artillery was to command knowledge. In this period, artillery design also began to anticipate the future industrial age. Machines for boring cannon barrels to exact tolerances appeared in foundries, driven by water or steam power. Precision manufacturing allowed longer barrels and higher pressures, which increased both velocity and range. The resulting feedback loop, better materials enabling better equations demanding better materials, drove the continuous refinement of artillery science. War became the testing ground for metallurgy, chemistry, and mechanics. Yet even as the tools of destruction grew more sophisticated, their rhythm remained slow and deliberate. A cannon still required a crew, careful loading, and precise timing. The smoke of black powder still hung thick in the air, obscuring the field. The act of firing remained an intersection of calculation and human coordination. In these moments, siege warfare still retained traces of its ancient lineage. The steady, deliberate work of engineers applying reason against resistance. By the close of the 18th century, the calculus of artillery had achieved a strange equilibrium. The weapons were powerful but not yet mechanized. The mathematics elegant but not yet automated. The balance between intellect and labor persisted. Sieges were now conducted with instruments and equations, but they still unfolded under the same sky, across the same earthworks as they had for millennia. What changed was the mind behind them. The siege engineer was now a scientist, his diagrams as rigorous as any astronomer's chart. In the measured silence that followed a bombardment, amid the acrid smell of powder, one could sense the convergence of centuries of inquiry. From the swinging rams of Assyria to the ballistics tables of Napoleon, every weapon had been a question asked of the material world, and every wall a reply. The calculus of artillery was not just the mathematics of flight, but the continuation of humanity's oldest pursuit, the search for control over energy, motion, and consequence. And the 19th century transformed siege warfare from a craft of calculation into an instrument of industrial science. The slow evolution of metallurgy, chemistry, and mechanics that had guided the age of cannon now accelerated under the pressure of steam, steel, and precision manufacturing. For the first time in history, the materials of war were produced not by artisans, but by machines. The siege engine, once an object of craftsmanship, became an industrial product, identical, standardized, and infinitely reproducible. At the center of this transformation was the Industrial Revolution in metal. The invention of the Bessemer process in the 1850s allowed molten iron to be converted into steel by controlled oxidation, producing material of unprecedented strength and consistency. Cannon barrels could now be cast longer, thinner, and lighter, withstanding greater internal pressure. Rifled barrels, grooved spirals cut into the bore, imparted spin to projectiles, stabilizing their flight and increasing accuracy over miles rather than hundreds of meters. The physics remained the same, but the precision multiplied. The age of geometry had given way to the age of metallurgy. Explosive shells replaced solid shot. Instead of relying solely on impact, shells carried timed or percussion fuses that detonated on contact or delay. Chemistry joined metallurgy as a partner in design. Gun cotton, nitroglycerin, and later TNT offered far more energy per weight than black powder. Each new compound demanded reanalysis of pressure, recoil, and trajectory. Artillery tables expanded again, now filled with logarithms, coefficients, and experimental data. The gun became a laboratory for both physics and chemistry. The wars of the 19th century demonstrated this convergence of science and industry with brutal clarity. During the Crimean War, the siege of Sevastopol in 1854-55 displayed both the endurance of old methods and the potency of new ones. Traditional earthworks and batteries still formed the structure of attack, but the guns were rifled, the logistics mechanized, and the calculations precise. Observers noted that the bombardments were less theatrical but more efficient. Measured sequences of firing, reloading, and adjusting, executed under centralized command. Each gun emplacement operated like a production unit, contributing to a coordinated system of pressure on the enemy's defenses. The American Civil War accelerated the process further. Railways allowed the transport of heavy artillery over long distances. Telegraphs transmitted firing orders and reports. At the Siege of Petersburg in 1864, both sides employed trench systems stretching for miles, anticipating the static front lines of the 20th century. Heavy Parrott rifles and mortars fired from fortified positions in continuous bombardment. The siege had become a system of logistics and communication as much as force. Energy, information, and supply were now inseparable. Behind these machines stood a new type of professional, the military engineer trained in both physics and production. Foundries became extensions of the battlefield. The same precision lathes and boring machines that produced locomotives and bridges were used to machine cannon. Drawings were standardized. Tolerances measured to fractions of a millimeter. The engineer's notebook replaced the artisan's intuition. Siege warfare became a discipline of data. Fortifications evolved accordingly. The star-shaped bastions of Vauban's era could not withstand modern artillery. engineers adapted by burying fortresses into the earth. Concrete, iron reinforced where possible, replaced masonry. Magazines were vaulted underground, casemates shielded by layers of soil and steel. Defensive firepower was integrated into the structure itself. Rotating turrets, armoured cupolas, and concealed gun ports allowed defenders to respond without exposing themselves. The fortress was no longer a wall, but a machine, self-contained and self-regulating. The forts surrounding cities such as Antwerp, Liège, and Verdun reflected this new design. They formed rings of subterranean power, each linked by roads and communications, calibrated for overlapping fields of artillery fire. Their geometry was less ornamental than functional, angles derived from ballistic range, not aesthetic proportion. This was engineering stripped of symbolism, a pure expression of energy management. Where the Renaissance fortress had symbolized rational order, the industrial fortress symbolized applied physics. The shift from individual craftsmanship to industrial repetition also altered the psychology of war. The sound of a single cannon had once signaled human presence, a crew, a commander, a decision. Now thousands fired in concert, their discharges timed by watch and telegraph. The battlefield became a coordinated system of mechanical impulses. Observation replaced intuition. Measurement replaced judgment. War had entered the realm of control theory, though the term would not yet exist. The lessons of siege warfare also influenced civil technology. Techniques developed for boring cannon improved the precision of hydraulic cylinders and steam engines. Experiments in propellant chemistry advanced mining and construction explosives. The study of stress and blast shaped early civil engineering standards. Every innovation born from destruction found a parallel in creation. The science of breaking walls became the science of building bridges. As the century drew toward its close, the balance between offense and defense seemed stable but deceptive. Rifled cannon and concrete forts appeared to have reached an equilibrium. Each could destroy the other only with great effort and cost. Yet beneath this apparent stability, chemistry and mechanics were moving toward a new disruption. The development of smokeless powder in the 1880s, based on nitrocellulose, eliminated the thick clouds that had once obscured battlefields, allowing accurate, sustained fire. The introduction of breech-loading mechanisms made reloading faster and safer. Firing rates increased, ranges lengthened, accuracy improved. The siege was about to transform again from methodical bombardment to industrial annihilation. By the dawn of the 20th century, artillery had become the dominant force in warfare. No longer confined to sieges, it defined entire fronts. The same principles that once governed the breaching of walls now applied to landscapes. The precision of steel and the chemistry of explosives extended siege logic across entire continents. The distinction between fortress and field began to blur. Every position could become a fortress. Every bombardment, a siege. Yet in this convergence of science and destruction, the continuity remained clear. The equations of motion, the control of energy, the measurement of stress, all echoed the same reasoning that had guided the builders of rams, trebuchets, and bastions. The tools had changed. The questions had not. How to store energy, how to release it, how to withstand it. These problems defined both the machines of industry and the weapons of war. As night fell over the great foundries and arsenals of the 19th century, their furnaces glowed like modern equivalents of the campfires that once ringed walled cities. Sparks rose into the air, illuminating steel shells and cast barrels lined in rows. The siege had become industrial, its rhythm mechanical, its science exact. Yet behind the noise of machinery and fire lay the same quiet curiosity that had always driven human invention: the desire to understand and command the forces of the world. By the early 20th century, siege warfare had become inseparable from chemistry. The industrial world's understanding of molecular structure and controlled reaction now determined the power of its weapons. The black powder that had once ruled battlefields was obsolete. It burned too slowly, produced too much smoke, and limited pressure within barrels. The new era of explosives was defined by compounds designed for specific energy release, stability, and detonation velocity. The siege weapon, reborn through chemistry, could now reach farther, strike harder, and destroy with precision unseen in prior centuries. The transformation began with nitroglycerin, discovered by Ascanio Sobrero in 1847, but too unstable for practical use. It was Alfred Nobel who stabilized it by absorbing it into diatomaceous earth, creating dynamite in 1867. This invention, meant partly for mining and construction, soon influenced military engineering. Tunnels and trenches could be excavated faster, and fortifications demolished with controlled charges. But dynamite also taught chemists how to manage violent energy, how to harness detonation rather than merely survive it. This understanding would define the explosives that followed. Nitrocellulose, developed into smokeless powder, replaced black powder in firearms and artillery by the 1890s. The result was transformative. Without dense smoke revealing positions, guns could fire continuously. The absence of residue reduced maintenance and allowed sustained barrages. Coupled with breech-loading mechanisms and recoil-absorbing systems like the French 75's hydraulic carriage, artillery became faster and more mobile. A gun crew could now fire dozens of rounds per minute with minimal repositioning. Each shot was an application of chemistry, physics, and mechanical design in perfect synchronization. TNT, trinitrotoluene, followed. First synthesized in 1863 but weaponized decades later, TNT's advantage lay in its stability. It could be melted and cast safely, stored for long periods, and detonated with precision. When combined with high-velocity fuses and rifled shells, TNT turned artillery into a weapon of geometry and chemistry. The projectile's shape, rotation, and timing were matched to the energy of the explosive within. Each shell represented a controlled experiment in molecular energy transfer. The First World War demonstrated the full consequence of this progress. The Western Front became a continuous siege, a 400-mile fortification of trenches, wire, and artillery. The distinction between field and fortress disappeared. Fortified positions extended across entire nations, and bombardment replaced maneuver. In battles like Verdun and the Somme, millions of shells were fired, reshaping the earth into a landscape of craters and shattered soil. The siege was no longer localized. It was continental. Every front line became a wall to be breached by chemistry and steel. Artillery dominated. Heavy guns such as the German 420 mm howitzers, nicknamed Big Berthas, reduced concrete forts to rubble within hours. Their shells, containing hundreds of kilograms of TNT, created shockwaves that pulverized masonry and fractured underground bunkers. But the true evolution lay not in the gun's size, but in their coordination. Fire was directed using aerial observation and mathematical plotting. Shell impacts were recorded, corrections applied, and new firing tables produced in real time. Siegecraft had become computation. For the first time, the relationship between weapon and landscape became dynamic. Artillery reshaped terrain, which in turn redefined tactics. Engineers studied soil composition, rock density, and moisture to predict blast effects. Craters could form instant defenses or obstacles. chemistry dictated geometry. The land itself became part of the system, a medium of both attack and resistance. The logistics of this era reflected the scale of industrialized siege. Ammunition factories operated continuously, feeding rail systems that transported shells to the front. Each shell required precise assembly, casing, fuse, explosive filler, and timing mechanism. Errors meant detonation during handling or failure in flight. Every success represented the convergence of thousands of calculations. Warfare had become a process chain, from molecular synthesis to ballistic trajectory. Behind the lines, fortresses adapted once again. Reinforced concrete, deeper tunnels, and armoured cupolas extended protection, but no defence was absolute. High explosive shells produced not only destruction, but pressure waves that propagated through earth and steel alike. Fort Douaumont at Verdun, thought to be impregnable, fell to German forces after internal explosions ignited stored ammunition. The lesson was chemical as much as tactical. No material could fully resist the molecular violence of modern explosives. Chemistry also altered the human element. Gas warfare, chlorine, phosgene, and mustard gas, extended the concept of the siege beyond physical barriers. The air itself became a medium of attack. Where once walls and gates defined the limits of assault, now the atmosphere carried destruction. Engineers and chemists designed shells not only to break stone, but to penetrate lungs. The line between weapon and environment dissolved completely. Even after the war, the science of explosives continued to refine itself. Research into detonation physics produced more efficient compounds, balancing stability and energy. Pentolite RDX and later Composition B offered higher brisance and shape charge potential. These advances would carry siege logic into the realm of armoured warfare, demolitions, and eventually rocketry. The same principles of stored chemical energy guided both artillery shells and space exploration. The underlying question, how to release energy precisely, remained unchanged. In the interwar period, military theorists attempted to reconcile this destructive capacity with mobility. Engineers developed self-propelled guns and mortars to support mechanized forces. Fortifications such as the Maginot Line embodied both faith and anxiety in engineering. Vast networks of steel and concrete designed to channel and delay the energy of explosives. Yet even as these fortresses were built, aircraft and tanks threatened to bypass them. The siege weapon was no longer fixed. It was becoming airborne and armoured. By the Second World War, chemistry had reached its culmination in military form. Explosives powered not only artillery, but rockets, torpedoes and bombs. The German V2, launched in 1944, was both a missile and a symbol, a continuation of the siege tradition translated into vertical dimension. It carried a 1-ton warhead across hundreds of kilometres, descending without warning. The same physics that had governed the trebuchet's arc and the cannon's recoil now described trajectories that extended into the stratosphere. As the war ended and the atomic age began, the science of explosives merged with nuclear physics. The principles of stored energy, confinement, and rapid release found their ultimate expression in fission. The siege, in its oldest sense, a struggle to break fortifications, became almost obsolete. No wall could withstand the detonation of atoms, yet the intellectual lineage was direct. Every bomb, from powder charge to nuclear device, represented the same chain of reasoning: measure, contain, and release. The age of explosives thus closed the mechanical history of the siege. Energy had moved from torsion to pressure, from combustion to chain reaction. The evolution was cumulative, each era preserving the questions of the last. And though fortresses crumbled and walls disappeared, the logic of siegecraft, control over matter, time, and force, remained embedded in every weapon and every calculation that followed. As night settled over the laboratories and proving grounds of the 20th century, the echoes of ancient engines still lingered. The trebuchet, the cannon, and the howitzer all spoke the same language of energy and trajectory. The materials had changed, but the purpose endured, to translate human intention into measurable power. The siege, now fought with molecules and equations, continued its quiet dialogue between invention and resistance. The 20th century's wars revealed that fortifications, though threatened by explosives and aircraft, had not vanished. They had simply migrated underground. The logic of protection persisted, now expressed through geology, reinforced concrete, and subterranean design. The old fortress walls had dissolved into the terrain itself. Defense no longer stood above the earth. It became the earth. The First World War was the laboratory for this transformation. As heavy artillery rendered surface structures untenable, armies dug down. Trenches, dugouts, and underground galleries replaced bastions and towers. Engineers rediscovered ancient principles of siegecraft, cover, angle, and depth, but reinterpreted them through modern materials. A trench was a negative wall. Instead of standing between attacker and defender, it removed the defender from view altogether. Protection became concealment. The Western Front's trench systems were complex works of civil engineering. Each sector contained communication lines, supply routes, and drainage systems. Reinforced dugouts housed command posts and hospitals. Barbed wire, machine gun nests, and observation points created interlocking defences. This was not a single wall but a network, resilient because it could absorb energy rather than resist it. The industrial fortress had dissolved into a distributed system. The same concept extended to permanent fortifications. The Maginot Line, constructed between 1929 and 1938 along France's eastern frontier, represented the culmination of centuries of siege logic. It was a fortress stretched across a nation. Interconnected bunkers, underground railways, ammunition lifts, and armoured turrets. Engineers calculated sight lines, firing arcs, and blast tolerances with mathematical precision. Air filtration and electrical systems allowed troops to survive days of bombardment. Every component was buried, redundant, and modular. The design philosophy was that of a machine built to endure energy rather than repel it. Its German counterpart, the Siegfried Line, followed similar principles, combining pillboxes, tank traps, and underground shelters into a continuous defensive field. Both systems embodied the faith that fortification could still neutralize firepower through engineering. Yet the Second World War proved otherwise. Mobility had outpaced fortification. Armoured columns and air power bypassed static defences, rendering the grandest sieges irrelevant. The Maginot Line's impregnable walls were never truly tested. They were simply avoided. This did not end the evolution of fortified earth. During and after the war, engineers refined underground design further, adapting it to withstand not cannon fire, but aerial bombardment. In cities across Europe and Asia, civilians and militaries alike constructed bunkers of reinforced concrete, their ceilings meters thick. Each bunker was a miniature fortress, engineered with shock absorption, pressure equalization, and internal support structures. The science of resistance had shifted focus. The enemy was now blast wave rather than projectile. The Cold War expanded this logic to continental scale. As nuclear weapons emerged, the siege problem inverted. No wall could resist atomic force directly, so protection became a matter of distance, depth, and redundancy. Entire command centers were built beneath mountains, such as NORAD's Cheyenne Mountain Complex in the United States and the Soviet Yamantau facility in the Urals. Civil defense planners calculated optimal depths, rock densities, and tunnel geometries to dissipate shock. Fortification became geophysics. The Earth itself was treated as a defensive medium, measured for compressive strength and seismic damping. These installations preserved the engineering lineage of the medieval fortress. They featured multiple blast doors, independent power supplies, filtered air systems, and compartmentalized design to prevent cascade failures. Each was a closed ecosystem, capable of sustaining life during extended isolation. In their silence and endurance, they echoed the ancient citadel. The difference was one of scale. The modern fortress was measured not in meters, but in megatons. Even outside the nuclear context, the concept of fortified Earth persisted. During the Vietnam War, the Viet Cong constructed elaborate tunnel networks, some extending for tens of kilometers. These systems, hand-dug yet strategically sophisticated, demonstrated that fortification did not require industry, only understanding of terrain. Entrances were concealed, routes booby-trapped, chambers ventilated through disguised shafts. Here the siege reversed entirely. The technologically superior force became the besieger, the hidden tunnels the fortress. Earth once again provided the ultimate defense. By the late 20th century, fortification and technology had merged completely. Hardened command centers, missile silos, and underground airfields continued the trend toward buried resilience. Engineers applied lessons from both civil construction and nuclear testing. Shock isolation, pressure wave modeling, and materials research defined design. Reinforced concrete was supplemented by composite armor and steel honeycomb structures. Blast physics became an exact science. Modern computing allowed engineers to simulate structural responses to explosions. Finite element analysis replaced empirical testing. Fortresses could now be designed virtually, their failure points predicted before construction. The principles remained constant: absorb energy, redirect force, preserve function. In this sense, the modern data center or underground laboratory continues the same lineage as a medieval keep. Both are enclosed systems designed to endure hostile conditions. Psychologically, too, the idea of the fortress endured. Even as warfare moved into cyberspace and orbit, nations still built shelters, bunkers, and protective perimeters. The instinct to fortify is older than siege engines. It is biological. Human survival has always depended on enclosing space, regulating entry, and controlling exposure. The evolution from wall to trench to bunker reflects not technological change alone, but an enduring mental architecture: security through separation. In contemporary conflicts, urban warfare has revived many elements of siegecraft. Cities themselves function as layered fortresses, their structures offering cover and concealment. The physics of modern explosives still meets the same countermeasures: angle, mass, distance, and absorption. Concrete barriers, rebar reinforcement, and modular blast walls repeat the principles of the bastion and rampart, now translated into urban geometry. The siege persists within the city's fabric. Seen from above, the continuity of this history becomes evident. Each generation redefines the fortress in response to its dominant form of energy. Stone walls resisted kinetic energy. Concrete resisted chemical energy. Buried structures resist thermal and shock energy. The process remains cyclical. Every weapon creates its countermeasure. Every countermeasure inspires a new weapon. The fortified Earth represents the current equilibrium, an architecture not of defiance, but of accommodation. As night falls over the modern world, the outlines of ancient fortifications are faint but still visible beneath the ground. Beneath highways and cities, beneath the data vaults and government complexes, lies the same impulse that built Jericho's walls and Constantinople's towers. The materials have changed, the threats multiplied, yet the reasoning remains constant. Energy meets structure, and structure endures through adaptation. In this buried continuity, the siege finds its final metaphor. The fortress no longer defines the boundary between armies, but between humanity and the forces it has unleashed. The earth itself has become both shield and witness, absorbing the shock of centuries of invention. The mechanization of warfare in the 20th century transformed siegecraft yet again. Where once energy was stored in ropes, counterweights, or chemical explosives, it now moved through engines of steel and combustion. Tanks, armoured vehicles, and mechanized artillery altered both offense and defense, integrating mobility with destructive power. The logic of the siege, the controlled application of energy against fortification, remained, but the instruments had become machines that could traverse terrain, breach walls, and concentrate firepower with unprecedented speed. Early tank designs emerged during the First World War. The British Mark I, deployed in 1916 at the Somme, combined armour plating with caterpillar tracks, allowing it to cross trenches and rough ground that had previously impeded infantry. These machines were slow, mechanically fragile, and vulnerable to artillery, yet their conceptual innovation was immense. They transferred force directly to the battlefield, eliminating the need for prolonged engineering work to approach defences. The siege, once a matter of positioning and preparation, now included mobility as a factor in energy application. Mechanised artillery reinforced this change. Self-propelled guns could be moved quickly to positions previously inaccessible, providing firepower where walls or trenches were assumed safe. Trucks, tractors, and rails integrated logistics with weapons deployment. The energy of gunpowder and high explosives was now paired with engines, allowing massed, flexible, and coordinated application. Siegecraft became not just calculation of angles and distances, but coordination of movement, timing, and mechanical reliability. During the interwar years, military theorists developed doctrines to exploit mechanized assault. J.F.C. Fuller in Britain and Heinz Guderian in Germany emphasized the integration of tanks with infantry and artillery in concentrated spearheads. Their concept was simple in principle, but revolutionary in execution. Mobility could bypass the static defences of fortifications entirely, rendering walls irrelevant. A siege could be redefined as rapid penetration, shock and disruption rather than attrition. Energy was no longer applied gradually. It was delivered in massed dynamic bursts. The Second World War demonstrated the full implications. Blitzkrieg, Germany's lightning strategy, employed combined arms to collapse fortified positions without prolonged bombardment. Artillery, tanks, and mechanized infantry worked in unison to exploit gaps, encircle resistance, and force surrender. Traditional sieges became rare exceptions. Fortifications such as the Maginot Line were bypassed. Industrial mobility replaced static defense. The principle of controlled energy, once expressed through walls and trenches, now moved across the battlefield itself. Yet siege engineering did not vanish. It adapted. Cities, bunkers, and fortresses still required neutralization. The Allies employed heavy artillery and specialized tanks to breach hardened positions. Tanks with flails or armor-piercing shells destroyed fortifications, while engineers placed demolition charges to collapse bunkers and walls. The process was mechanized, precise, and reliant on both human coordination and mechanical power. In this context, the siege had become a system combining mobility, force, and calculation. Armoured vehicles also transformed supply and logistics. Ammunition, fuel, and materials could now move alongside the fighting force, reducing delays inherent in historical sieges. This integration allowed sustained pressure on enemy positions, extending the operational range of mechanised attacks. The ability to deliver energy consistently over distance reinforced the old principles of siegecraft: application of force with precision, persistence, and adaptability. In parallel, aerial technology augmented siege methods. Aircraft introduced vertical energy projection, able to bypass walls entirely. Bombing campaigns, such as the destruction of Rotterdam or Monte Cassino, applied explosives from above, rendering traditional horizontal fortifications ineffective. The siege now encompassed 3 dimensions: land, subterranean, and aerial. Engineers responded by reinforcing ceilings, building shelters, and designing dispersal systems to absorb and redirect energy. The fortress became volumetric rather than planar. Mechanized assault also demanded new approaches to defense. Anti-tank obstacles, minefields, and layered fields of fire were integrated into fortifications. Mobility and energy application were anticipated in design. Traps, berms, and counter-mobility measures echoed the logic of the medieval moat and ditch, but adapted to armoured vehicles. Defence had become dynamic, combining anticipation, absorption, and channeling of force. The engineering of mechanised siege operations extended beyond military applications. Construction machinery, excavation, and demolition methods evolved directly from techniques developed to overcome fortified positions. Cranes, bulldozers, and hydraulic systems allowed energy to be directed efficiently, echoing centuries of siege logic in civilian form. The line between destruction and construction, once symbolically distinct, now reflected the same underlying principles: energy applied with calculation, precision, and control. By the late 20th century, the concept of siege had transformed again. Static fortifications remained vulnerable to combined arms. Mobility dictated the tempo of engagement. Energy was no longer localized to walls, but distributed across terrain, vehicles, and projectiles. Yet the intellectual lineage persisted. The siege was still a problem of energy management, now expressed through engines, explosives, and movement rather than stones and timber. Mechanized siege warfare represented a fusion of centuries of innovation. Physics, chemistry, mathematics, and engineering converged in a single operational concept: the deliberate, controlled, and sustained application of destructive force to overcome resistance. The principles that guided Assyrian engineers, medieval carpenters, and Napoleonic gunners were embedded in the tracks of a tank, the trajectory of a shell, and the placement of an obstacle. Human ingenuity had mechanized itself, but the logic of the siege remained unchanged. As dusk settled over the battlefields of the mechanized era, the silhouettes of armoured vehicles and artillery pieces stretched across the landscape. Each machine embodied centuries of accumulated knowledge: leverage, energy storage, trajectory, fortification, and persistence. The siege had become a dance of motion and force, a testament to humanity's capacity to translate understanding into action. Yet despite the speed and power, the fundamental question endured: how to convert energy into effect with precision and control. The expansion of siegecraft into the aerial domain marked a profound evolution. Aircraft, first experimental in World War I and perfected in World War II, introduced a new vector for energy application. Where traditional siege relied on horizontal approaches, artillery lines, sapping, and mechanical engines, planes delivered explosives vertically, circumventing walls, trenches, and fortifications entirely. The fortress, once designed to resist physical impact along its perimeter, now faced threats from above, demanding innovations in both materials and design. Observation balloons in the First World War had already demonstrated the advantage of height. Artillery could be adjusted based on real-time reconnaissance, and supply routes could be monitored from above. Pilots flying early aircraft added precision, identifying weak points and guiding artillery fire with increasing accuracy. Air power transformed siege logic. Information became part of the energy system. Position, trajectory, and timing could now be coordinated over distances and dimensions previously inaccessible. By World War II, air-delivered ordnance had reached unprecedented sophistication. Strategic bombing campaigns targeted industrial centres and fortifications alike. Heavy bombers like the B-17 and Lancaster could carry tons of explosives across hundreds of kilometres, dropping them with carefully calculated timing and spread. The science of ballistics extended to aerial release. Altitude, velocity, wind drift, and explosive yield were all factored into operational planning. The siege was now as much about mathematics and meteorology as it was about brute force. Precision-guided munitions, emerging in the mid-20th century, epitomised this fusion of technology and calculation. Laser-guided bombs, GPS-guided missiles, and smart artillery shells allowed destructive energy to be applied with extraordinary accuracy. A single projectile could neutralise a fortified structure without collateral destruction to surrounding areas. The principle remained consistent with centuries of siegecraft: maximise effect while minimising wasted energy. Yet now the application was not limited to human strength or black powder. It was guided by sensors, computers, and feedback loops. Airborne tactics also reshaped defensive architecture. Roofs were reinforced, anti-aircraft emplacements added, and dispersal techniques employed. The emphasis shifted from resisting impact to controlling exposure. Underground facilities, bomb shelters, and reinforced command centres were designed to absorb vertical energy, often in ways analogous to Vauban's angled bastions. Material science became central. Concrete mixtures, steel reinforcement, and shock-absorbing layers were engineered to exact specifications. Defence had become predictive, modelling the behaviour of projectiles before they arrived. Simultaneously, airborne platforms allowed logistical and operational flexibility. Paratroopers and gliders could deploy behind enemy lines, bypassing conventional walls and fortifications. The siege problem expanded. It was no longer only about breaching physical structures, but about controlling territory and movement across three-dimensional space. The mathematical and engineering principles of positioning, timing, and concentration of force now included altitude and trajectory as variables. The integration of air power and artillery led to combined arms tactics. Forward observers in aircraft directed artillery barrages with precision previously impossible from ground observation alone. The energy applied by shells and bombs could be synchronized with mechanized assaults, overwhelming defenses through coordinated, multi-dimensional application. Siegecraft had evolved into systems engineering, simultaneous attack, observation, and adaptation, optimized through data and real-time calculation. Technology also extended the range of siege effects. Rockets and missiles could strike fixed fortifications thousands of kilometers away. Civilian infrastructure, once considered invulnerable due to distance or terrain, became potential targets. The traditional fortress, the bastion city, the Maginot Line, or underground bunker now faced challenges that could not be entirely mitigated by walls, concrete, or earth. Defense required anticipation, mobility, and intelligence, as much as strength. The logic of the aerial siege influenced post-war military planning and civil engineering. Research into blast dynamics, structural resonance, and shock propagation informed urban construction, bridge design, and nuclear survivability studies. Every calculation made to neutralize a fortification contributed to broader understanding of materials, energy distribution, and human safety. The siege had moved from localized destruction to systemic knowledge application. Despite these advances, fundamental principles persisted. Energy had to be stored, directed, and released with precision. Vulnerabilities had to be measured and exploited. Forces had to be applied in a controlled, calculated sequence to achieve maximum effect. The medium had changed, from rope, torsion, and masonry to aircraft, explosives, and guidance systems. But the problem remained the same: overcoming resistance efficiently. In the early 21st century, precision continues to define siegecraft. Drones, autonomous systems, and satellite-guided munitions represent extensions of centuries-old reasoning. Sensors replace human observation, algorithms replace trial and error, and digital feedback replaces visual confirmation. Yet even in this high-tech environment, the siege retains its ancient rhythm: identify, calculate, apply, and absorb. The logic of the past underpins the technology of the present. As dusk falls over modern airfields and testing ranges, the shadows of bombers, drones, and guided missiles stretch across tarmacs and deserts. The silhouette of the fortress persists in bunkers, command centers, and hardened shelters, but the methods of assault are now invisible to the naked eye. Explosives, energy, and mathematics intersect silently above, continuing a dialogue that began with stones, ropes, and the slow arcs of trebuchets. The airborne siege represents the latest chapter in an enduring story: humanity's persistent pursuit to measure, control, and overcome resistance. In the 21st century, the concept of siege expanded into the digital domain. Physical walls, artillery, and underground bunkers now coexist with networks, servers, and encrypted systems. The principles of siegecraft, observation, calculation, and controlled application of force, remain unchanged, but the medium has shifted. Energy is no longer measured in kilograms of explosive or tons of stone, but in data packets, bandwidth, and computational cycles. Fortification exists in code as much as in concrete. Cyber fortresses operate on principles analogous to historical defense. Firewalls, encryption, and intrusion detection act as ramparts, bastions, and moats, each layer designed to absorb or deflect attacks. Redundancy and compartmentalization mimic the overlapping fields of fire in a Vauban-style star fort. Data centers employ physical and digital safeguards, from reinforced structures to multi-factor authentication. The siege problem has become a question of access, speed, and persistence. Attackers must penetrate sequential layers, while defenders monitor and respond in real time. The offensive side applies energy through targeted actions: malware, denial of service attacks, phishing campaigns, and code exploits. Timing, precision, and adaptation are critical. Just as an artillery battery requires calculation of trajectory and charge, a cyber operation requires understanding of network topology, system vulnerabilities, and response times. Each action is measured, its effects monitored, and adjustments made continuously. The principles of controlled energy application, honed over millennia, now govern digital strikes. Historical concepts of reconnaissance remain vital. Reconnaissance in cyber operations takes the form of network mapping, penetration testing, and intelligence gathering. Attackers survey the system, identify weak points, and plan the sequence of action. Observers and automated monitoring tools act as aerial scouts did in previous centuries, feeding real-time data to direct interventions. Feedback loops ensure that responses can be recalibrated, creating a continuous interplay between offense and defense. Redundancy in cyber defense mirrors buried bunkers, overlapping trenches, and multi-tiered fortifications. Distributed servers, mirrored databases, and failover systems ensure that breaches in one node do not compromise the entire network. Data flows are rerouted dynamically, much like defenders redirecting artillery fire to compensate for a damaged bastion. Energy applied to a single layer may be absorbed, dissipated, or deflected entirely, emphasizing the importance of system-wide coordination. Attackers also employ principles from the physical siege. Precision targeting, sustained pressure, and exploitation of weak points are central. Social engineering functions as sapping, indirect, patient, and aimed at undermining the structural integrity of human operators rather than code alone. Automated attacks function as artillery barrages, capable of overwhelming defenses if sustained. The combination of human insight and machine power echoes the integrated operations of mechanized assaults. The rise of cyber fortresses has blurred traditional boundaries between military, civilian, and commercial domains. Banks, energy grids, hospitals, and communications networks all represent potential fortified positions. Their defenses are technical, but must also anticipate human behavior, operational procedures, and supply chains. The siege, therefore, encompasses both tangible and intangible elements. Fortification has become an ecosystem, simultaneously physical, logical, and social. Just as historical fortresses evolved to absorb chemical, mechanical, and explosive energy, modern cyber fortresses are designed to withstand computational and informational energy. Load balancing, rate limiting, and threat modeling dissipate digital pressure. Patch management, auditing, and system monitoring ensure resilience over time. The underlying logic is identical to that of medieval ramparts. Control exposure, absorb force, and maintain function under stress. The cyber domain also introduces an element of invisibility. Unlike artillery or explosives, energy is applied without immediate visual or sensory feedback. Success and failure are determined through indirect measurement, data flow, system logs, or network latency. This abstraction challenges defenders and attackers alike, yet the methodology remains consistent. Observe, measure, apply, and adapt. The siege becomes a process of understanding systems at multiple levels and acting with precision. International conflict now demonstrates that cyber sieges can have strategic effects equivalent to conventional attacks. Disruption of infrastructure, theft of information, or manipulation of communications can influence entire populations, economies, and military operations. The scale of impact mirrors that of massive historical sieges, but the medium is intangible, instantaneous, and global. The principles of physics and energy transfer are replaced by logic, code, and network dynamics, yet the strategic intent remains unchanged. The lineage of the siege is evident in cyber operations. Observation, geometry, redundancy, energy application, and adaptation are applied not to walls and moats, but to servers, protocols, and human networks. Lessons from centuries of physical warfare inform modern defense planning. Architects of cyber fortresses study stress, flow, and containment as rigorously as their counterparts once studied stone, timber, and gunpowder. As night falls over data centers and server farms, their blinking lights trace the outlines of a new battlefield. The energy coursing through fiber optics and circuits mirrors the trajectory of artillery shells and the shockwaves of explosives. Fortresses endure, though they are now virtual. Attacks persist, though they are now invisible. The siege continues, translating centuries of human ingenuity into a domain where observation, precision, and control determine survival. While land fortifications and cyber defences evolved, the principles of siege persisted at sea. Coastal fortifications, naval artillery, and blockades applied the same logic of energy, geometry, and persistence to maritime contexts. From the cannons of early modern forts to the massive coastal batteries of the 20th century, engineers adapted siegecraft to the interaction of land, water, and vessel. The medium changed, but the principles remained. Observe, calculate, and apply force with precision to breach or deny access. The first permanent coastal batteries appeared in the Renaissance, responding to the threat of cannon-armed ships. Forts were positioned to cover harbours and channels, often constructed with angled bastions to optimise overlapping fields of fire. Their walls were thicker and lower than inland fortresses, designed to absorb impact rather than resist it directly. Artillery was arranged to create crossfire zones, where attacking ships would be exposed to concentrated energy over distance. Geometry and physics dictated both the placement and orientation of guns. Naval vessels, in turn, adapted to this static defence. Hulls were reinforced, gun calibers increased, and manoeuvrability emphasised to reduce exposure. The exchange became a dynamic interplay. Ships applied concentrated energy to breach walls, while forts absorbed, deflected, and redirected force. The principles of siege were expressed through relative motion and the careful measurement of trajectory. Range tables, wind corrections, and elevation calculations were essential. Miscalculations could lead to wasted fire or catastrophic failure. The 17th and 18th centuries saw the refinement of coastal siegecraft. Vauban himself designed fortifications at Brest and other French ports with integrated water batteries. His designs considered tides, river channels, and angles of approach, optimizing both firing positions and defensive coverage. Attackers now required coordinated naval bombardment, combined with landing operations. The siege had become a system involving terrain, energy, and timing. Industrialization magnified these dynamics. Rifled naval guns, larger caliber shells, and steam-powered ships increased the range, velocity, and destructive power of coastal sieges. Concrete and reinforced masonry replaced stone in fortifications, while hydraulic mechanisms allowed more precise gun aiming. Observation posts and optical rangefinders extended engagement distances, allowing fire to be calculated with scientific precision rather than guesswork. The principle remained consistent: absorb energy strategically and apply concentrated force to exploit weaknesses. Blockades represented a different type of siege. Instead of concentrating destructive energy on walls, attackers restricted access to supplies and reinforcements, forcing surrender through attrition. Naval blockades during the American Civil War, World War I, and World War II demonstrated that energy in a siege could be applied indirectly through control of resources and movement. Coastal fortifications had to be integrated with supply management and surveillance to resist both kinetic and systemic pressure. Submarine warfare added further complexity. The stealthy application of energy beneath the waterline forced new defensive measures. Anti-submarine nets, minefields, sonar detection, and mobile escort formations. Coastal fortifications had to consider three-dimensional threats, blending traditional artillery with modern technology. Engineers calculated detection ranges, firing arcs, and structural vulnerability in ways reminiscent of terrestrial bastions, but translated into fluid, dynamic environments. The logic of energy absorption persisted in the design of modern coastal defences. Sloped walls, reinforced concrete, and underwater obstacles dissipated kinetic energy from shells and torpedoes. Batteries were dispersed to prevent simultaneous neutralization. Redundant communication and observation networks allowed defenders to respond even when some positions were compromised. This approach mirrored the layered, overlapping fields of fire perfected in Vauban's fortresses, applied to the sea. Naval sieges also required integrated systems of offence. Coordinated bombardments, amphibious landings, and logistical support relied on timing, observation, and precise application of energy across multiple platforms. Success demanded the same combination of calculation, endurance, and adaptability seen in historical land sieges. Even as technology advanced, the operational principles endured. The 20th century added aerial reconnaissance and missile technology to coastal sieges. Aircraft could spot targets beyond visual range, and missiles allowed long-range precision strikes against hardened fortifications or anchored vessels. The integration of sensors, communication, and energy application created a multi-dimensional siege environment. Coastal defence became an exercise in systems engineering, where observation, calculation, and energy distribution determined outcomes. In the 21st century, the concept of coastal fortification continues in new forms. Radar installations, missile batteries, and naval bases embody the same logic as stone walls and bastions. Control approach: concentrate defensive energy and deny access. The medium has shifted from cannonballs to guided missiles, from timber and stone to reinforced concrete and electronics, but the problem remains consistent. Human ingenuity continues to measure, anticipate, and redirect energy to maintain control. Viewed across centuries, the maritime siege demonstrates continuity and adaptation. Geometry, timing, redundancy, and precision govern outcomes, whether in a 17th century harbour or a modern naval base. Energy must be directed and absorbed strategically. Observation guides application. Resilience derives from design as much as strength. The fortress, whether inland, underground, or coastal, remains an enduring concept, a system designed to convert energy into effect while preserving function. As twilight descends over coastlines and harbours, the silhouettes of batteries, bunkers, and ships trace the evolution of siegecraft across water and land. Waves lap against walls, once bombarded by cannon and now observed by satellites. The principles that guided medieval engineers and Napoleonic gunners persist, translated into metal, concrete, and circuitry. The siege, like the sea, is a constant force, reshaping strategy, technology, and human understanding of energy. The contemporary battlefield increasingly exists within urban landscapes, where the principles of siege are applied to streets, buildings, and subterranean networks rather than isolated fortresses. Cities, with their dense construction and layered infrastructure, present unique challenges and opportunities for both attackers and defenders. The logic of controlled application of force, observation, and adaptation remains constant, but the scale and complexity of obstacles have multiplied. Urban fortifications are both intentional and incidental. Streets lined with reinforced buildings act as corridors and barriers. Apartment complexes, industrial warehouses, and transportation hubs create choke points. Defenders exploit verticality and concealment, establishing observation posts and firing positions from rooftops, windows, and basements. The energy of attacks must be calculated to account for reflection, absorption, and channeling through concrete, steel, and glass. Mistimed or misapplied force can produce unpredictable results, including structural collapse or civilian casualties. Modern siege operations in urban areas require integration of multiple technologies. Ground forces coordinate with drones, satellite imagery, and remote sensors to map terrain, monitor movement, and direct precise application of energy. Explosives are carefully calculated to neutralize target structures while preserving critical pathways for movement and supply. In this environment, the principles of geometry, ballistics, and controlled energy are applied in real time, often with iterative adjustment as conditions change. Tunnels, subways, and utility networks create subterranean fortifications reminiscent of the sieges of old. Insurgents, defenders, and urban planners alike use these spaces for concealment, storage, and protected movement. Breaching or neutralizing these hidden networks requires specialized knowledge of engineering, chemistry, and physics. Explosives, flooding, ventilation control, and monitoring systems are all employed to control the energy applied within these complex environments. The siege becomes a three-dimensional problem. Historical siege tactics, including sapping and mining, find new relevance in urban warfare. Attackers may undermine structures using explosives or controlled demolition, while defenders reinforce walls, block access, and establish internal redundancies. Observation and information flow are crucial. Every blind corner, line of sight, and structural feature affects the trajectory of both projectiles and personnel. Modern urban sieges thus resemble intricate puzzles where both sides manipulate energy and space simultaneously. The evolution of precision-guided munitions has altered the calculus of urban assault. Missiles, artillery shells, and aerial bombs can be directed to specific floors, rooms, or structural components. This precision reduces the need for prolonged bombardment, but increases the demand for accurate intelligence and coordination. The principles of observation, calculation, and energy application remain identical to those developed for medieval and industrial sieges, though the medium has shifted from stone and timber to concrete, steel, and electronics. Civilian infrastructure introduces additional constraints. Hospitals, water treatment plants, and power stations impose limits on where force can be applied. Siegecraft now incorporates risk management, ethical considerations, and collateral analysis. Attackers must direct energy efficiently, while minimizing unintended consequences. These considerations introduce new dimensions to classical problems: how to achieve effect while respecting constraints, and how to exploit vulnerabilities without compromising essential systems. Defense in urban environments often relies on layered strategies. Buildings are fortified internally, critical assets are dispersed, and mobility corridors are blocked or rerouted. Sensors, cameras, and networked monitoring systems act as early warning devices. Redundant power, communication, and logistics channels maintain operational resilience under sustained attack. These principles echo historical fortresses. Overlapping layers, redundancy, and controlled application of force create resilience and extend the capacity to resist. The dynamic nature of urban environments requires continuous adaptation. Streets, bridges, and buildings can be rapidly altered, creating new obstacles or opportunities. Commanders and engineers must calculate effects quickly, adjust plans, and deploy resources where energy can be applied most effectively. The siege becomes iterative: observe, measure, apply force, evaluate, and adjust. Feedback loops are essential, reflecting a centuries-old understanding that static plans are insufficient when energy meets complex resistance. Urban siege operations illustrate the convergence of multiple historical threads: artillery and explosives, mechanized mobility, observation from elevated and aerial positions, and cyber-based coordination. Each innovation amplifies the others. Mobility allows concentrated application of energy. Observation allows precise targeting, Technology increases the scale, speed, and persistence of both offense and defense. The city, like the fortress of old, functions as both obstacle and system for energy management. Ultimately, urban siegecraft demonstrates the continuity of human ingenuity. Walls, barricades, streets, and tunnels continue to shape the application of force. Observation, geometry, redundancy, and controlled energy remain central. Technology has changed, but the core problem, the need to measure, direct, and absorb energy effectively, remains unchanged. Modern cities are fortresses in the abstract, and the siege continues within their streets, high-rises, and subterranean networks. As evening falls over contemporary cities, lights flicker across buildings and roads. Sensors, drones, and command centers hum quietly, reflecting the ongoing interplay of observation, calculation, and controlled energy. The principles that guided engineers and soldiers centuries ago, geometry, persistence, and adaptation, remain in operation, translated into steel, circuitry, and software. The urban siege exemplifies the enduring dialogue between human innovation and the forces it seeks to control. Looking across the span of history, it becomes clear that siegecraft is defined less by specific weapons or fortifications than by an enduring logic. The measurement, management, and application of energy against resistance. From the first battering rams and slingstones to modern missiles, drones, and cyber operations, each innovation represents a new method to solve the same fundamental problem. The siege, in every era, is an exercise in controlled force, observation, and adaptation. Early engineers learned to store and release energy mechanically, using torsion, tension, and leverage. Ropes, counterweights, and wooden frameworks amplified human strength, translating effort into effect. Observers calculated trajectories, angles, and timing. Defenders responded with walls, moats, and overlapping fields of fire, absorbing and redirecting energy through geometry and material. These principles form the foundation of siegecraft. Energy must be measured, the environment understood, and effect maximized through control and precision. The introduction of gunpowder and later high explosives shifted the medium but preserved the logic. Kinetic and chemical energy replaced mechanical tension. Calculations expanded to include pressure, combustion, and shock waves. Fortifications adapted, becoming thicker, lower, and often buried to absorb these new forms of energy. Siege became increasingly scientific, a fusion of physics, chemistry, and engineering. Each shell, cannonball, or charge represented a controlled experiment in energy transfer. Industrialization and mechanization further transformed the field. Steam, steel, and engines enabled mobility, massed firepower, and precise coordination. Artillery became faster and more powerful, while tanks and armoured vehicles applied energy across terrain previously impassable. Observation from aerial platforms added vertical perspective, extending the principles of the siege into 3 dimensions. The intellectual core remained: plan, measure, apply, and adapt. The 20th century expanded siegecraft into multiple domains simultaneously. Air power, armoured mobility, subterranean fortifications, and naval operations demonstrated that energy could be directed from any vector, constrained only by physics, observation, and calculation. Precision and timing replaced brute force in many cases, though massive energy application continued to shape landscapes, cities, and populations. Redundancy, dispersion, and controlled absorption became central to defensive strategy. The emergence of cyber fortresses illustrates the most abstract extension of these principles. Walls, moats, and bastions are replaced by firewalls, encryption, and network segmentation. Energy becomes computational, information-driven, and sometimes invisible. Observation and feedback guide the application of force in real time, mirroring the centuries-old methods used to breach masonry and timber. Siegecraft has become less a matter of physical destruction and more a test of systems understanding, resilience, and adaptation. Urban environments blend all historical threads. Streets, buildings, tunnels, and networks function as obstacles and fortifications simultaneously. Modern operations integrate mechanized assault, aerial observation, precision strikes, and cyber coordination. Attackers and defenders alike must calculate effects across multiple dimensions, using both technology and strategy. The siege has become a system-level problem, requiring integration of observation, energy, and adaptive response. The unifying theme across eras is continuity. Every fortress, battery, trench, or server cluster embodies principles of redundancy, geometry, and energy absorption. Every attack, whether by trebuchet, cannon, tank, missile, or code, follows the same logic. Identify weak points, concentrate force, apply with precision, and adapt in real time. Human ingenuity has always sought to understand the forces it must overcome, whether those forces are physical, chemical, mechanical, or digital. Even as technology evolves, the challenges remain consistent: measurement, control, persistence, and adaptation. Siegecraft is less about the materials of war and more about systems thinking. Observation informs application, calculation guides force, redundancy preserves resilience. Every advance in offense generates a response in defense, and every new defense provokes further innovation. The siege is a continuous dialogue between creation and destruction, understanding and application. Reflecting on this continuum, it becomes evident that siegecraft is a mirror of human problem-solving. It embodies curiosity, analysis, and creativity applied to resistance. Whether constructing a ram, calculating an artillery trajectory, or designing a cyber defense, humans have consistently translated understanding into controlled application of energy. Knowledge accumulates, technologies evolve, but the intellectual structure endures. As night spreads across landscapes, cities, and networks, one can trace the quiet lineage of these principles. Walls of stone, concrete, and steel, trajectories of stones, shells, and missiles, streams of data flowing invisibly through cyberspace, all represent attempts to manage force, resist intrusion, and achieve effect. The siege, though expressed in countless forms, persists as a demonstration of the same fundamental reasoning: the deliberate, controlled, and precise application of energy against resistance, shaped by observation, calculation, and adaptation. The story of siege weapons, from ancient battering rams to digital fortresses, is ultimately a story of human ingenuity. It is the evolution of strategy, science, and engineering in pursuit of understanding the interaction between energy and resistance. Every advance, every innovation is a link in a chain connecting past and present, material and abstract, physical and informational. In this continuum, the siege remains an enduring testament to humanity's capacity to measure, control, and shape the forces it confronts.